Hello, welcome back to my lecture. My name is Jahrul Alam. Today I'm going to talk about spectral method for differentiation. The idea is to utilize a Fourier transform in mathematical modeling or numerical simulation. So let's look at very simple idea that we want to take this function sine of 2 pi x over L defined from minus L by 2 to L by 2, and we know that this function has a derivative given by this quantity that we can calculate that, and its second derivative is given by this quantity written here. Okay, so what I will do is that I will follow the Fourier transform method. I'm not going to derive Fourier transform method in this lecture. Let's assume that I have this function ux. When I do Fourier transform, I get u hat k, and I calculate this. Then, in order to find the derivative, the beauty of a Fourier transform method is that derivative becomes just multiplication. So what we do is we calculate the Fourier transform of the quantity u by using first Fourier transform, multiply by I k u k hat. So where I is the complex unit and k is the frequency or wave number. So you take the frequency, multiply the Fourier transform, and then do an inverse Fourier transform. What you get is the derivative. This is very accurate numerical technique and very easy to apply in any of the programming language that we have currently have. So similarly, if we have the second derivative, then we take the Fourier transform, which is uk hat, calculate the Fourier transform, and then multiply this by ik twice. So for the first derivative we multiply by ik, and you want to get the second derivative, multiply for a second time, and for a second time multiplication I know that I square equals minus 1, so we just write minus, and then k times k is k square. Take the inverse Fourier transform, and then we get the second derivative. Okay, so the theory is very simple, nice, and for modeling simulation purpose at this stage we may not need the details of the derivation. So let's go back to see if we can write some code to implement those derivatives. So here in this code, I have just a standard input statement in Python. So I have imported numpy, matplotlib, and well, scipy is not needed for this demonstration. So let me just comment out that. Okay. So I have defined this function in a domain minus L by 2 to L by 2, where I have this L is 50, and I have taken 1024 grid points. So in this line here, I generate the grid. So I just call np dot linspace. This is very standard command, and I just remove the endpoint. So keep in mind, for Fourier differentiation, we are going to assume that the function is defined either in the real line or it is on an interval and it is periodically extended to the real line. And for this periodic extension, we just don't need the endpoint. So one point is removed. That is internally handled by the FFT algorithm. So then I have here defined my function u of x, np.sine 2 times pi times x by L, and I have defined my exact first derivative ux, exact second derivative uxx. Those are very standard approach. Now the important point here is the frequency k. So I have defined here in my code kx, where in my note I mentioned it is k. So the wave number in Fourier transform goes from something minus to something plus. So the ranges goes from a negative and positive. And when we do the Fourier transform, we arrange the frequencies in a way that we first put the positive frequency and then we put the negative frequency, and then we scale it. So the positive frequency is going from 0 up to n by 2 minus 1, and then the negative frequencies are going from negative n by 2 up to 1. Okay, so and then in NumPy we can take those two ranges and concatenate them together putting one after one. That's very straightforward, and then we rescale it by 2 pi divided by L. Okay, so that's keep in mind. Two things we have to keep in mind is that when we generate the grid, we remove the endpoint, and then we have to carefully generate the frequency domain where we put the positive frequency in the first half and the negative frequency in the next half of my array, and then rescale it by 2 pi divided by L. And then we calculate the first derivative, which is the complex unit I times k times FFT. So we stored this into du hat in this code, which is the derivative in Fourier domain. Okay, and then you see that here I take the inverse Fourier transform and then take the real part, because inverse Fourier transform will be the complex number, so we just need the real part. So I get the first derivative, and similarly I calculate the second derivative. So negative k squared times u hat k, where u hat k is np dot fft dot fft. So NumPy FFT package, take the NumPy FFT package and then apply the first Fourier transform FFT on u, multiply by k square, and then I take the inverse Fourier transform. Okay, so let's first try to plot that. See if I can plot the first derivative. So save the code, and I'll be just using the Python command. That's not that important which way you run it. So the first derivative for the exact, which is the red color, and for the numerical, which is the black color, and they match as well. Let's go back and check the second derivative. And run the code again. Okay, and then again I have compared the first derivative and the second derivative and the matches together. So hopefully this code illustrates how to apply numerical technique in Python using the NumPy package to implement numerical differentiation with using Fourier method. Thank you very much. Thank you for watching.